All right. Greetings, YouTube. Beautiful mind here. Let's see. So, greetings, students. Hope everyone is doing well. Hope everyone had a great weekend and happy National Star Wars Day. May the 4th be with you. Let's see. So, we're actually entering the home stretch. I'm just trying to check my audio. Give me a moment. All right, sounds good. But yeah, so we're entering the home stretch. We have right at about 2 weeks remaining in the quarter. Let's see. So I think I went on and loaded all assignments for the rest of the quarter. Keep in mind that we get unlimited attempts. This group seems like they're doing pretty well. Like I know I've had a lot of you before. I hope you're all doing well. You all should be graduating. I don't know how that's going to go. I haven't gotten any information on that. I don't know what that's going to look like with this whole COVID thing. But, life goes on. We find a way. And, these things will work themselves out. I'm really proud of you guys. Like I said, we're entering the home stretch. I did go ahead and load. I think the final exam is loaded. Everything is loaded, right? So what that means is we get unlimited attempts at all assignments, okay? Late penalty is like at 10%. So you can honestly still get an A on all assignments if you really want it. Yeah. So the final submission for all assignments is Saturday, May 16th. And then the final exam, I'm going to let that stay open until the last minute of our last class. So the following Monday after May 16th, 17, 18, it says Monday, May 18th at 2:50. Everything will lock up, right? Even the final exam. So that's when our last official class time is. So all assignments are going to have them scheduled to lock out on that Saturday, May 16th, except for the final. The final will be open until the end of class time on that Monday, May 18th at 2:50 p.m. But like I say, the final exam, old exams, old quizzes, all the homework, all of that stuff is available now. And, anything that's late, again, the late penalty, I reduced the late penalty from 20% to 10%, okay? Also on Moodle, let's be sure that, let me see, we've completed the participation and honesty quiz. I think most of you all have. Also, there is an assessment on Moodle that we need to do. So that's going to, this participation and honesty quiz along with the assessment, those are going to be I'm going to submit those as quiz grades, okay? So aside from the work on Pearson and those 2 quizzes on Moodle, I really can't think of anything else, okay? So this week, I just want to take some time to move into chapter 5. We'll go ahead and let 5.3 be the last of the new material. So we'll just do a section a day. That'll close out for week 7. Most people in this class are fine. So yeah, I just want to do sections 5.1, 5.2, and 5.3, and we'll wrap it up. Okay. So, idealistically, integration is like a very important part of calculus. Given the time constraints of working in a quarter system, we can do the best that we can do. But it's a very, very important topic in calculus. It's like the other half of calculus. So we've kind of did some exploration with derivatives, and derivative being the slope of the tangent line at a point, and some applications of derivative. So now with integration is like the reverse of distributing. Given a function, and we take the derivative, and we'll produce another function that'll tell us the slope of the tangent line at any given point. So now, suppose we start with the derivative, and we want to work backwards and get a sense of the original function. That's what integration is. So integration is like reverse is the opposite of taking a derivative, like taking a derivative in reverse. Okay. Again, it's a very important topic, and we'll do the best we can with the time that we have remaining. I don't really want to go beyond section 5.3, just because we're on a quarter system and we're almost out of time. Okay, so we'll do a section a day, and we'll do the best that we can. All right. So let's see what it's looking like today. So we want to move into chapter 5 of integration. I want to read this chapter preview real quick. So we're now at a critical point in the calculus story. Many will argue that this chapter is the cornerstone of calculus because it explains the relationship between 2 processes of calculus, differentiation and integration. We begin by explaining why finding the area of regions bounded by the graphs of functions is such an important problem in calculus. Then we'll see how antiderivatives lead to definite integrals, which are used to solve the area problem. But there is more to the story. We will also see the remarkable connection between derivatives and integrals, which is expressed in the fundamental theorem of calculus. In this chapter, we develop key properties of different integrals, investigate a few of their many applications, and present the first of several powerful techniques for evaluating definite integrals. Okay. So, let's see, we have the section 5.1 area under curves. The derivative of a function is associated with the rate of change and slope of tangent lines. We also know that antiderivatives or indefinite integrals reverse the derivative operation. Okay. So, given a function, if we take the derivative, that'll give us the slope of the tangent lines. But if we integrate a function, well, we're going to see where that goes, right? So the area under a velocity curve. Consider an object moving along a line with a known position function. We learned in previous chapters that the slope of the tangent line to the graph of the position function at a certain time gives the velocity at that time. We now turn the situation around. Suppose we know the velocity function of a moving object. What can we learn about its position function? Okay. So imagine a car traveling at a constant velocity of 60 miles per hour along a straight highway over a 2-hour period. The graph of the velocity function v equals 60 on the interval from 0 to 2 is a horizontal line. The displacement of the car from 0 to 2 is found by a familiar formula. So the displacement is going to be the rate times time. So 60 miles per hour for 2 hours is going to be 120 miles. This product is the area of the rectangle formed by the velocity curve and the t-axis between 0 and 2. In this case, we see that the area between the velocity curve and the t-axis is the displacement of the movement object. Okay, so look, if we look at this figure 5.2, we have our velocity function, right? So if we think about the displacement of the car, if we're going at 60 miles per hour for 2 hours, it's going to be 120 miles. So then if we consider the area under the curve of our velocity function, so notice that the area under the curve is the basic shape is a rectangle. So if we say the length times the width, 60 times 2 gives us 120, which is the displacement, right? So because objects do not necessarily move at a constant velocity, we first extend these ideas to positive velocities that change over an interval of time. One strategy is to divide the time interval into many subintervals and approximate the velocity of each subinterval with a constant velocity. Then the displacement of the subinterval are calculated and summed. This strategy produces an approximation to the displacement. However, this approximation generally improves as the number of subinterval increases. So what it's saying is, like, given a curve and we want to approximate the area under the curve, we can approximate the area basically by creating a bunch of like rectangles. We'll see it in action. This is called like the Riemann-Sum technique, I think. Let's look at it. So approximating displacement. Suppose the velocity in meters per second of an object moving along a line is given by this function. Velocity is going to be equal to the t squared, where t goes from 0 to 8. Approximate the displacement of the object by dividing the time interval 0 to 8 into n subintervals of equal length. On each subinterval, approximate the velocity of the constant equal to the value of v, evaluated at the midpoint of the subinterval. So for part A, we're asked to begin by dividing 0 to 8 into two subintervals, 0 to 4 and 4 to 8. Okay, let me see. On each subinterval, approximate the velocity with the constant speed equal to the value evaluated at the midpoint, right? I kind of want to see, I have an idea in my mind. I kind of would like to see how they wrote it. Let's go like this. So if we think about the graph, we have v equals t squared. That's a parabola. That's a basic parabola, right? So if we look at it from 0 to 4, the midpoint, so I'm gonna just do a rough sketch. So just a rough sketch. Let me see, 0 to 8. Let's plot some points. 1, 2, 3, 4, 5, 6, 7, 8. This will be the positive x. And then let's just go. I kind of want to go by tens. I'm gonna go by tens. I'm gonna go 10, 20, 30, 40, 50, 60, 70, 80. That's fine. Positive y. 90. 10, 20, 30, 40, 50, 40, 50, 60, 70, 80, 90, 100. Okay. So then if we look at the graph, right? If it's x squared, when x is 1, y is 1, then we have what, 2, 4? It's about there. 3, 9, 4, 16, 5, 25, 6, 36. About there. 7, 49, 8, 64. And that's about what they wanted, right? So from here to here, right? So we're considering from here to here. So for part A, they want us to divide 0 to 8 into two subintervals, 0 to 4 and 0 to 8, right? Let me add a page. Let's see. So if we look at 0 to 4, the midpoint from 0 to 4 is going to be 2. Okay. So let's do it like so if we're considering this part, right? I know, let's undo. Let's go like this. So 0 to 4, but we're going to approximate it using 2. And then let me fill that with purple, right? So the area under that curve, so we have 0 to 4, and we're going to use it based on the midpoint, which is when x is 2. So the area under that curve, right? Lift times width. So that's 4, and that height is what? 4? 4 times 4 is 16. So that area, the area under that curve is 16 here, right? And then if we do from 4 to 8, let's use another color. We'll do this color. Halfway is what? 6? 6 squared is 36. Let's fix that a little bit better. Okay. So we're going to go from 4 to 8. And then the area under the curve is at 36, which is there, all right? We're going to do this one in orange. Okay. So we have what? 4 times 36? 120 plus 24, 144. So the area under this curve is 144, right? So then if we add those together, so this is example 1A. If we said the 16 plus the 144, 154, 160, it's approximately. So our claim is that the area under the curve is approximately 160. Let me see. Okay, I just want to look at this answer because I just want to see how they're presenting it. Yeah. No, that's not it. We divide 0 to 8 into two subintervals, 0 to 4 and 4 to 8, each with length 4. The velocity of the subintervals is approximately divided at the midpoint. So 0 to 4 at 2, so we get 4 meters per second. And so the displacement is 16 meters. We approximate this, so 144 meters. Therefore, the approximation to displacement over the entire is going to be 160 meters. Okay, this is fine. So our reasoning is fine. Okay, so then let's do B. Divide into 4 subintervals. Okay, so if that was 1A, let me do this for example 1B. I'm going to get a copy of this. Copy, paste. Okay. 4 subintervals, right? Okay. So the first one goes from where? 0 to 2. So the midway is what? 1? Okay. So let's do it this way then. So if we do from 0 to 2, so then we're going to use what? We're going to say v of 1. So that's going to be what? 1 meter per second. So then the displacement is going to be 2 times what? 1? I don't know why I'm writing it that way. So then the area under the curve, right? 2 times 1 is 2 meters. So if it's moving at 1 meter per second for 2 seconds, it's gonna be displaced by 2 meters. Okay. So then let's do from 2 to 4. So then that means we're gonna find v of what? 3. 3 squared is gonna be 9 meters per second. So, and it's going for what? 2 seconds. Yeah, so then the displacement is going to be what? 9 times 2 should be 18 meters. Okay. So then let's do from 4 to 6. So that means we're going to do what? V of 5, which is going to be 25. So 25 meters per second. So then we're going to say 25 times 2 seconds is going to be 50 meters. That's the displacement there. And then we do from 6 to 8. Okay. So we're going to do, if we use the midpoint, it's going to be v of 7, which is going to give us 49 meters per second. And then we're going to say that 49 times 2 seconds is going to be 98 meters, right? So then the total displacement is going to be what? 2 plus 18 plus 50 plus 98, which is 7168 meters for part B. For part A, we got 160 meters. And then 8 subintervals, right? So for part B, we got 168. Let's go ahead and do this last one. Okay, this is fine. So then example 1C. So if we're doing 8 subintervals, so the first subinterval is going to be from 0 to 1. So then we're going to do v of, what is it, a half? So we 1/4 meters per second. So then 1/4 times 1 second is going to be 1/4 of a meter. Okay. And then from 1 to 2 seconds, that means we're going to use, what is that, 3 halves? It's going to give us 9/4 meters per second. So then it's going to be, well, all of these are going to, since these are all for 1 second, we can just take those answers, right, for all of them. So then if we go, let's see, 1 to 2, so then we can go 2 to 3. It's going to be what, 5/3? Sorry, 5/2. 25/4 meters per second. Okay. And then, the units are just going to be meters because we're multiplying by 1 meter. Okay. Time in 1 second, sorry. We're multiplying by 1 second. So then it's going to give us just that many meters. If we do from 3 to 4, it's going to be the velocity is 7 by 2. It's going to give us 49 by 4. Okay. And then 4 to 5. Oops. 9 by 2. 81 by 4. 5 to 6. 11 by 2. 121 by 4. 6 to 7. 13 by 2. 169 by 4. 78. Daggone it, why do I keep doing that? 7 to 8. 15 by 2. I think that one is 225. Hey Google, what's 15 times 15? Okay. All right. So then if we add all these up, we're going to have what? 1 by 4 plus 9 by 4 plus 25 by 4 plus 49 by 4 plus 81 by 4 plus 121 by 4, 169 by 4, 225 by 4. Okay. 10, 35, that would be 80, so that's 79. 80 and 80 is 160. 160, 200, 280, 281, 281, 281, 381, 441, 450, 450, 650, 675. I think that's 675 by 4. Let's go ahead and get that number. So there's a 1 into 27 is what? 635. So then 8. Something's not right. Hang on. Trying to do too much in my head. Let me get this number proper. How many 4s are in 6? There's a 1. The remainder is what? 2. 27. So 7 times 4 would have been 28. So it has to be a 6. It's 24. The remainder is 3. So it has to be an 8. Oh, 32. That's what I was messing up on. The remainder is 3. So 0.75. Okay. 168.75. Okay. Meters. Okay. All right. I feel like these are good. Okay. So then if we look at here. So where's the conclusion of all of that? So these graphs are essentially what was going on, right? We drew out the first one. We started to draw the second one, then we stopped. But these are all based on the midpoints. Okay. Okay. So like when the n was 2, you see we have the 2 rectangles, right? Then when the n is 4, we have the 4 rectangles, and we found the sum of the areas of those rectangles. And then n was 8, we had 8 different rectangles, and we found the sum. So the progression of example 1 can be continued. Larger values of n mean more rectangles. In general, more rectangles give a better fit to the region under the curve. So with the help of a calculator, we can generate the approximations in table 5.1 using n equals 2, 4, 8, 16, 32, and 64 subintervals. Observe that as n increases, again approximations. Observe that as n increases, the approximations approach the limit of approximately 170.7 meters. The limit is the exact displacement, which is represented by the area under the region. This strategy of taking limits of the sum is developed fully in section 5.2. Okay. Okay, let's look at this right here. So, a definition of a rectangular partition. Suppose we have a closed interval AB, again, is a closed interval containing n subintervals, okay, of equal length, some delta x, so some b minus a over n, where a is x naught and b is the final endpoint. The endpoints x naught, x1, x2, so on and so on, of the subintervals are called grid points, and they create a rectangular partition of the interval AB. In general, the kth grid partition is going to be given by this. Okay. In the kth subinterval, we choose any x point. Let me see, Riemann sums. Let's see. I'm going to go here. Okay, let's look at what do we mean by this definition of Riemann sums. So suppose f is defined on a closed interval AB, which is divided into n subintervals equal length, delta x. If x sub k star is any point on the kth subinterval, okay, for k going 1 to n, then this expression is called the Riemann sum. It's called, this sum is called a left Riemann sum if x sub k star is the left endpoint. It's called a right Riemann sum if x sub k star is the right endpoint, and it's called a midpoint Riemann sum if x sub k star is the midpoint. Is any point on the kth subinterval, okay, for k goes from here, okay. So then we have f of x sub 1 star times the change of x. So then we have these points in the subinterval. So you saw when we constructed ours earlier, we let the x sub k star be the midpoint, right? But we can do the same thing using the left endpoint or the right endpoint, or apparently any point on the kth on each subinterval, right? Just be consistent, apparently. So we got a left Riemann sum. So where instead of using the midpoint, suppose we use the left endpoint from that subinterval, then it would be a left Riemann sum, and similar for the right Riemann sum. Okay. So you see in this left graph that we're using all the left endpoints, and then in the middle graph they're using the right endpoints to construct the rectangles, and then the last graph they're using the midpoint to construct the rectangles. Okay. So we have this example. So let R be the region bounded by the graph of f of x equals 3 times the square root of x. So you know the graph of square root of x is the top half of a sideways parabola. When we multiply the outside by 3, it does a vertical stretch by a factor of 3. So you should already have an image of this graph from college algebra. And the x-axis between 4 and 16. Approximate the area R using a left Riemann sum where we break it up into 6 subintervals. Illustrate the sum with the appropriate rectangle. So we could draw this. Approximate the area using the right endpoints. It's basically the same thing, but using the right endpoints. Do the area approximations in part A and B. Underestimate or overestimate the actual area under the curve. Okay. Oof. I think I just got sleepy all of a sudden. Let's see. Sun is going to be coming up soon. All right. So 4 to 16, what is that? 12? Okay. I just kind of want to see how they were writing it first, just for format purposes. Okay, I see. I think I'm gonna just do it my own way. I could follow what they're doing, but I'm gonna just do it my own way. Okay. So let's see. So this is what, example 2a. We have this f of x equals 3 times the square root of x, right? And we want the x to go from 4 to 16, right? So if it's a total of what, 12? So if we want to divide it into 6 subintervals, 12 divided by 6 is going to be 2, right? So we should do from what, 4 to 6. All right, if we do from 4 to 6, and if we're going to use the left Riemann sum, so we're going to use the left endpoint. So if we're going to make a rectangle using that left endpoint, so we need to find f of 4, right? That's going to give us our y, and then our x's. I think all the x's are going to be what, 2 in this case, because it goes from 4 to 6, right? So then the square root of 4 is 2, so it's going to be 6 times 2, so that one should be 12, right? So then if we do from 6 to 8, we're going to use f of 6, that's the left endpoint, times, that's the y, and then the x is still 2, so then that's going to be 3 times the square root of 6 times 2. That's going to be 6 to the power of 1 times 6 to the power of a half, 6 to the 3 halves, whatever that number is. I have to use a calculator. Yeah, let me go ahead and use my calculator. So 6 times the square root of 6. So approximately 14.7. Okay. So then if that's 6 to 8, let's do 8 to 10. So then we're going to do f of 8. And the change in x is going to be 2 in this case. So that's going to be 3 times the square root of 8 times 2. So I'm just going to use a calculator for that as well. Come on. 6 times the square root of 8. So I'm just going to say approximately 17. Okay. So if we do, what's the next one? 10 to 12. It's going to be f of 10 times 2. So basically it's going to be, what, 6 times the square root of 10. So approximately 19. (12 to 14). So we're going to do f of 12 times 2. That's basically going to be what? 6 times the square root of 12. So then 20.8. Okay. Mm-hmm. And then we're going to do what, from 14 to 16. So we're going to do f of 14 times 2. It's going to be 6 times the square root of 14. We'll say 22.4. Okay. So then, if we add all these together, so then we're going to say what, 12 plus 14.7 plus 17 plus 19 plus 20.8 plus 22.4. 1, 2, 3, 4, 5, 6. Okay. 12 plus 14.7 plus 17 plus 19 plus 20.8 plus 22.4. Okay, these add up to 105.9. Okay, so that was using the left endpoint. Approximate the area of R using a left Riemann sum. Okay. Okay, so let's do B using the right endpoint. So then example 2B. So we still have the same subintervals, but now instead of using the left endpoint, we're going to use the right endpoint. Okay. So this first one, it's basically, let me see, so we're going to do what? F of 6 times 2. Ultimately, it's going to be 6 times the square root of 6, all right? So approximately 14.7. Oh, duh. 14.7, right? Did we do that one already? Square root of 6? Okay, so I think all of these we did, because then we're going to have what? F of 8 times 2. We're going to have F of 10 times 2. We're going to have F of 12 times 2. We're going to have F of 14 times 2. And we're going to have, now this one I know we didn't do, F of 16 times 2. Okay. F of 8, we said was what? 17? So that one was approximately 17. And then 19, 20.8. After 10, it should be 12, right? And then 22.4. And then let's get to 20. F of 12, 20.8. F of 14, 22.4. Okay, and then we didn't do the 16, so we need to do the 16. It's going to be 6 times the square root of 16. Square root of 16 is 4, so that was going to be 24, right? So then if we add these together, we'll get 14.7 plus 17 plus 19 plus 20.8 plus 22.4 plus 24. 1, 2, 3, 4, 5, 6. So it should be the same as the last, but we need to subtract out the 12. So we're going to say if we subtract the 12 and add 24, then we can add 12 to that answer. No, not that answer. Not that one. So let's just change that 12 to 24. Okay, 117.9. So that one is 117.9 approximately, or that's what those add up to. Okay. So do the areas in parts A and B underestimate or overestimate the actual area under the curve? Did we do the midpoint? It looks like that the left one might underestimate and the right one might overestimate. That's what it looks like. Okay, let's see. So they got 105.876. We got, yeah, that's fine. And then the second one, 117.876. Cool, that's fine. That's what we got. So then it says, looking at the graphs, we see that the Riemann sum in part A underestimates the area of R, whereas the right Riemann sum in part B overestimates. Therefore, the area of R is between 105 and 117. These approximations improve as the number of rectangles increases. Okay. Let me see. Man, we've been going at it for like 40 minutes. Oh my goodness. That's how mathematics is, though. It just you just kind of get lost in the sauce, and next thing you know, you blink and like all this time has gone by. You're like, what in the world is going on? What in the world of Carmen Sandiego? Okay, anyway, so hopefully that made sense, right? So we constructed our rectangles in the first one using the left endpoint. The second one was the right. So we see that one was an underestimate, the other was an overestimate. So we know that the actual area of the curve, the area under the curve, is somewhere between those two results that we got. And so the more rectangles that we take on this interval, the better our approximation will be. Oh, I think I am getting spent. Let's look at this example 3. Okay. It says, oh, I don't like that. Hang on. There it is. Oh, come back. Go back. Crap. Okay, that's better for me. It's whatever. All right. So now let's look at this example 3. Okay. So midpoint Riemann sum. Let R be the region bound by the graph of this, and let the x-axis be between 4 and 16. Approximate the area of R using a midpoint Riemann sum with 6 subintervals. Illustrate the sum with the appropriate rectangles. I just don't feel like doing this. I'm just being lazy. Okay. Let's see. Let's go here. Let's go to paper. Let's go like this. Okay. So we're essentially doing the same thing. Can we paste? Nope, that's not where I needed the page to be added. And now it's not working properly. Almost there. That's irritating. All right. Give me a moment. I'll be right back. And we're back. I think that fixed it. I don't know what I did, but it looks fixed. And then we don't need this page, right? Okay. Yeah, the app was kind of glitching a bit. Okay. So basically they're asking to do the same thing, but use a midpoint Riemann sum, right? So this first one, the midpoint is what, 5? So we're going to say what, f of 5 times 2 So that's going to be 3 times the square root of 5 times 2, which is going to be, and I'm just going to use my calculator. All right. 6 times the square root of 5. 6 times the square root of 5. 13.4. So this is approximately 13.4. So then this one is going to be what? F of 7 times 2. So it's going to be 6 times the square root of 7. And then this was going to be F of 9 times 2. 6 times the square root of 9. F of 11 times 2. 6 times the square root of 11. F of 13 times 2. 6 times the square root of 13. And then F of 15 times 2. So it's going to be 6 times the square root of 15. Okay. 9 is 3. 18 is this one. So we're going to say we got square root of 7, 15.9, square root of 11, 19.9, 6 times the square root of 13, 21.6, square root of 15. 23.2. Okay. All right. So then if we add these up, these add up to, we got 13.4, 15.9, 9, 18, 19.9, 21.6, and 23.2. Okay, 112. Okay, what did we get before? We said it was between. Yeah, between 105.9 and 117.9, and we got 112. That's promising. Okay, I don't think we need that extra page. Delete. What's my time? We've been going at it for about 50 minutes. Okay. All right. All right. Did I lose my? Oh, there it is, the 112. But I lost that. Where's that? This thing is totally glitching. I don't know where it went. I'm gonna just go like this. Okay. Okay, 112 approximately. So comparing the midpoints, figure 5.14 with the left and the right suggests that the midpoint sum is a more accurate estimate of the area under the curve. Yeah, I totally forgot about the microphone. I hope you're not wearing headphones. My bad, guys. All right. So, let me see. What's the time? Let's see. So estimate the area under the graph on the interval 0 to 2 using the left and right Riemann sums, where we break it up into 4 subintervals, where f is continuous but known only at the points in tables 5.2. Okay. let's go like this. All right. So let's see. We're going from 0 to 2 into 4 subintervals. So 0 to 1, so 0 to 0.5. Here comes the sun. Sun is coming up. So if we're breaking 0 to 2 up into 4 subintervals, 0 to 1, so we have 0 to a half. Then we have what? A half to 1. Then we get 1 to 1.5. Then we get 1.5 to 2. That's the 4 subintervals, right? Left and right. So left endpoint, right? So we're going to say, I guess we could write it, let's just do it. I like the way we've been doing it. So this is going to be f of 0, and then the change in x is going to be, all of these are going to be times a half. So then f of 0, that's going to be, so ultimately this is going to be a half. The left endpoint here, this is going to be f of a half times a half. So that's going to be 3 by 2. This is going to be f of 1 times a half. 2.25. 2 1/4. 9 by 4. And then f of 1.5 times a half. 1.5 is 5.5. 2.5, so 2.75? I think that's right, 2.75. Let me do half of 5.5. 2.75, okay. So this is using a left, this is a left sum. So we say 0.5 plus 1.5 is 2.25. It's 2.75. So that's 2, 4, 6, 7. Okay. Let's do the right Riemann sum. So I'm going to take that same partition. So then this one's going to be what? F of 0.5 times 0.5. It's going to be f of 1 times 0.5. F of 1.5 times 0.5. And f of 2 times 0.5. Okay. 0.5 is 3. So then this is going to be 1.5. F of 1 is going to be 9 by 4, 2.25. F of 1.5 was the 2.75. And then f of 2 is 6. Half of 6 is 3. So then we're going to do 1.5 plus 2.25 plus 2.75 plus 3. Let me see. 1, 3, 5, 8, 9.5. Okay. All right. So we did the left Riemann sum, we did the right Riemann sum. So we got what? 7 for the left, 9.5 for the right. So we know the area should be between those two. 7. With only 5 function values, these estimates of the area are necessarily crude. Better estimates are obtained by using more subintervals and more functional values. Okay. Give me just a moment. Okay, so working with Riemann sums is cumbersome with large number of subinterval. Therefore, we pause for a moment to introduce some notation that simplifies our work. We want to talk about the sigma or summation notation used to express the sums. Okay, when we did college algebra, we introduced this notation here, this symbol. So for example, the sum 1 plus 2 plus 3 up to 10 is represented by the sigma notation as this here. Right? So this symbol is red. The sum as k goes from 1 to 10 of k, right? So what this means is let k be 1 plus k2, 1 plus 2 plus 3 plus 4 plus 5 plus 6, and we stop when we get to 10. So we start when k is 1, and we stop when k is 10, and this symbol just means add up your answers, right? It just means add up your answers. Let's see, so right here, the symbol here, sigma, is a Greek letter capital S, stands for sum. So in this context, it means add up your answers. The index k takes on all integer values from the lower limit k equals 1 to the upper limit of k equals 10. The expression that immediately follows the summand is evaluated for each value of k, and the resulting values are added up. Okay. So the sum of powers of integers. Let n be a positive integer and c be a real number. So notice that there's no k here, but we're repeating this process n times. So c added to itself n times is going to be n times c. Notice we have a k here, so this is going to be when k is 1 plus when k is 2 up to n, and that's going to be given by this, right? N times n plus 1 over 2. If we have k squared, n times n plus 1 times 2n plus 1 over 6. Okay, so these are the sum of powers of integers. Okay, let's look at this. So left, right, and midpoint Riemann sums and sigma notation. Suppose f is defined on the closed interval AB, which is divided into n subintervals of equal length. If x sub k star is a point on the k subinterval, then the Riemann sum for the three cases arise in practice. So the left Riemann sum, if we're going to have as k goes from 1 to n, f of x sub k sub star, for instance, before we were doing the left endpoint times delta x. This is a left Riemann sum if x sub k star is going to be equal to a plus k minus 1 times delta star. I don't know where that second part comes from. I mean, if I think about it, I'm sure I can figure it out, but I'm just going to let it be. Oh, a plus k minus 1 delta x should be the left endpoint k, right? So 0 times, and then, yeah, the right Riemann sum. So this is basically forcing it to the left endpoint of that subinterval. This is forcing it to the right endpoint of that subinterval. And then this is going to force it to the midpoint. Okay. Evaluate the left, right, and midpoints of the Riemann sums for this using 50 subintervals. Make a conjecture about the exact area. What's my time? Okay. How many more? Okay, we're almost done. Let's see. With n equals 50. Okay, so we had those shortcuts for the sum of integer powers. Okay. So we probably could use that. Evaluate the left, right, and midpoint Riemann sums for this function from 0 to 2 using 50 subintervals. Okay. So let's focus on the left one first, right? That's funny. Let's focus on the left one first, right? I'm totally I think I'm like sleep talking. Okay, let's work here. Okay. So this is what example 5. Say we're focusing on the left Riemann sum, right? So it should be the sum as k goes from 1 to n, f of x sub k star times delta x. That's fine. Let's see. Here it is. We have our f of x is x cubed plus 1. Our a is 0, our b is 2, and we want our n to be 50. So for instance, let's verify that that force is the left endpoint. So if we have 0 to 2, we break it up into 50 subintervals. So the first one should be, the first k value, x sub k star, should be 0, right? So if this is the first one, right? So let's see, what is our first x sub k star? It should be 0. So then our a is 0 plus, if this is the first one, so we're going to say 1 minus 1, and our change in x, so what, we have 2 divided by 50 is 1 by 25. Okay, notice that this is 0. Let's verify the next one, right? So if we do 0 to 2, we divide it up into 50 subintervals. So the first subinterval should run from 0 to 1 by 25. The next one should run from 1 by 25 to 2 by 25. So the next point to test should, the next x sub k star should be 1 by 25, right? So since I think the first k was 1, right? So that was the first one. Let's do the second one. It should be a, which is 0, plus, now we're going to do 2 minus 1 times 1 by 25. And indeed, that's 1 by 25. Okay. Yeah, so that forces it to the left endpoint of each subinterval, right? That part on the right. Let's see, with this, so then for our case, it should be the sum as k goes from 1 to 50 in this case, f of x sub k star. So we're going to say this x sub k star cubed plus 1, that times delta x. What's that change in x here? Is 1 by 25. Okay. So we can actually do some manipulating here, right? This is going to be the same as the sum as k goes from 1 to 50. Let's see, does that help us? Well, we can distribute that 1 by 25, x sub k star cubed plus the sum as k goes from 1 to 50 of 1 by 25. Okay, so I distribute it and, apply the property. If we're adding those up, we can break it apart in this fashion. We can actually do a little bit more. We could say 1 by 25 times the sum as k goes from 1 to 50 of x sub k star cubed, right? Let's make that k a little bit better. I mean, that was a good k, but, let's minimize confusion here. And then that second part is just going to be 50, right? Yeah, 50 times 1 by 25, because we're adding the 1 by 25 to itself 50 times, right? So earlier we said the sum of integer powers right here, that power of 3, is going to be n squared times n plus 1 squared over 4. So n squared, that's going to be 50 squared times 51 squared over 4. Is that right? Did I read that right? And then we're going to say that times 1 over 25, okay, plus what, 2. Okay. Okay, we can do some simplifying here. It's least divisible by... let me write it this way before I'm going to just write it the way that helps me. So we're going to say 50 times 50, 51 times 51, I'm out of space, 25 times 4, plus 2 is still there. So now in this form, that turns, both of these are divisible by 2, so that becomes a 2, that becomes a 25. This cancels this. This turns this into a 25. Okay, that's what I was trying to see. So then ultimately we'll get 25 times 51 squared plus 2, which is, I'm going to have to use my calculator at this point. I don't have to, but you know, I can do it by hand, but I'm just not doing it by hand. I'm totally like keep myself awake. I mean, it's exciting and I enjoy it, but you know, it is like 6:48 in the morning. It's all good though. Squared plus 2. Let's see, what do we get? 65,027. Is that a reasonable answer? 65,027. Okay, let's see, how do we do? Let me go back and look at the context. Area under the curve, 0 to 2. I feel like we made it. Oh, okay. Let me see. Let me go back. Let me look at my numbers because I'm not confident in that answer. Okay. The left sum, that times that. Did we distribute that 1 over 25? We did. We did that. Yeah. That's 2. Mm, 25 times 4, right? 2, 25. Those are gone. That becomes 25. Okay. Let's just go with it and see what happens, right? Yeah, let's just go with it. 0 to 2. Wait a minute. I feel like I'm missing something somewhere. Okay, I think I'm gonna just go with it. Let's see, how do we do? So I got this. I can't find any errors. I'm not confident in the number, but I can't find any errors. So let's see. 1 over 25. We got that. Oh, here it is. Yeah, I didn't think that the answer made any sense. Let me see. What am I missing? Did I forget that one somewhere? Yeah, let me look at it again. We got to find our error. We're missing something. That's 100, right? Maybe we didn't use the proper formula. Let's go back. Okay, x cubed plus 1. A is 0. So 2 divided by 50 is 1 by 25. That's fine. Some of those. Delta x. Now we could just factor that out. it should be the same thing though. That one was 2, that one was fine. I know I could do that. 1 to 50 XOK star. I think that's where we made a mistake. Okay. Is that for each one? Okay, I think I see what I did. What I did wrong. So for each K, right? Okay, so right there. So the XOK star. Oh, okay. So we can go ahead and solve for those XOK stars. So they plug that in. That's fine. F of that. Did they actually calculate that? No, it's there. Okay, so I'm gonna go back. Let me see. So for the midpoint, we let XOK star be this, which is that, which is this. The value of the sum is going to be this minus 0.2. Okay, let me. Yeah, this is what I did, right? Yeah, there it is. Okay. Okay, so right here. 50, 51. Powers, and we find that this is 50. This, substitute the values of these sums into the right. Over 4, right? 50 squared times 51 squared over 4. So let me see. Yeah, we got that. So right here, right? This. Dang, we're like right there. There's something that I'm missing, but we're not far off. Let me go back. Let me try one more time. I always get stuck on the last one. Like, I think I just be like burning out and I'll be trying to go all the way. Let's look at it one more time. What are we missing here? Each one of those times that. So it's going to be each of those times that. So I kept it there, right? It's there. That one was 2. We got our 50 squared times 51 squared over 4. Let's divide by 100, right? Did I not divide by 100? But I did. Let's see. If we... Is that cubed? X cubed plus 1, right? X cubed plus 1 times 1 over 25. That's not being cubed. No, if I divide by 100, it doesn't fix it. Mm-hmm. Mm-hmm. So the sum from 1 to 50. Oh, the x of k. I just plugged in k. I see. Okay. I think I'm seeing it. I'm trying to follow the second one. I think I see where I made a mistake. K goes from 1. So it's my x of k that I'm not choosing properly. Find that this is equal to that. Is a plus k times, that's for the right. So if we're working the left, we got to find each of those. The sum of those, do they add up to that? Is 0.4 times k. Okay, so we got to convert the x of k. We have to actually apply it. Okay, that's where I made my mistake. Okay, so when I did my Riemann sum, I just plugged like k was 1. I just did 1 cubed and that kind of thing. I have to first evaluate the x of k. So it says it's only true if we're doing the left. That means the x of k should be given by that. So that's what we need to apply. Okay, I found it. I was like, yeah, I knew something. I was like, that number was way too big for what we were doing. Okay, that's how these things go. Man, I just be making mistakes left and right. Let's add a page, okay? So we got to go back right. So before we do that, I like to leave my errors. So what I'm going to do, because I think it's important, like you have to realize that, you know, we're all human in this, right? I'm going to strike through this. I'm going to go like that. I'm actually going to shrink it down just to get it on one page. Let's go here. I found, but yeah, that's not working either. Okay, that's fine. All right. So that's where I made mistakes. So let's go back right here. And I'll do this in like a little bit different color. So let's copy this. Let's pick up from right here. I think this is where we need to fix it. Let's copy and paste. Okay. So then from here, right? We're not at the point, we have to evaluate the x of k. That's where we made the mistake, right? So if we're doing a left endpoint, here it says that the x of k is going to be a plus k minus 1 times delta x. Let me write it here so I can see it. So again, because we're doing a left endpoint, x of k star should be a plus k minus 1 times delta x. We got to get this in terms of k. Right, we did it in terms of x. Let's copy. Let's cut this actually. Okay, so we need to evaluate that x of k. Let's paste. All right. So, okay. So then our x of k star, because we're doing a left endpoint, is going to be a, which is 0. We're going to keep the k minus 1, and our delta x is 1 by 25. Okay. So then this becomes, let's see, we got that 1 by 25 times k minus 1 by 25. Okay, I feel like this is better. So now if we take this and plug it in to our Riemann sum, now we get 1 by 25. Hopefully that's not an extra one. The sum, as k goes from 1 to 50, now we're going to have, do we have an extra one in there or not? I'm going to say that we don't. I'm going to just go with how the numbers are playing out. So if I factor out that 1 by 25, that's going to make, oh, it feels like I got an extra one now. I'm going to look at one other thing because I'm trying to minimize, I'm trying to like wrap it up. Where did we leave off? Do they get it squared? They don't. I think we do have an extra one. Let's see. Maybe not. Okay, let's just go with what we have. Let's go with how the numbers are coming out and see what happens. So if we go with how the numbers are coming out, we can factor out that 1 by 25, and so essentially this one is going to become squared, and it's going to leave us with, we got a k minus 1 inside, and we still got that plus 2. No. Let me back up. So we transform the x of k star into this thing here. Let me just write the whole thing. So then we get this 1 by 25 k minus 1 by 25, but then that's going to be cubed, all right? Okay. Plus 2. Something is getting away from me here. Okay. Let's cube in a binomial. That's not going to make it any better. We're almost there. Like, it's so irking me. That can go here. That will just be 50. That's fine. And it's at x of k cubed. So let's see. I want to see their alternative again. Right here. F of x of k. Okay. So that's going to be f of that thing. Okay. Okay. So first they converted the x of k star into its simplified form, then they plugged it in f of x. I was trying to plug the simplified into after the fact. Okay, so I think I might just start this one over because we're right there, but the order in which I did it, I think is what's throwing things off. So what I'm gonna do, I'm gonna get rid of this, and I want to go back. I want to go back to here. We got that. That's fine. Right here. Let me start here. Let me get a copy of this and this. No. Let's get a copy of this, and this. Let's copy. Okay, let's try it again. Let's go here. All right. So now, because we're doing a left sum, we can take, where'd it go? I got rid of it. Okay, so this one, right? X of k star is going to be, we have this a plus k minus 1 times delta x. Because we're doing the left endpoint, we can use this. Let's cut. Okay, I'm going to scrap all that and let's paste here. Okay. So let's go ahead and do this f of k sub star. Let's do this x of k star. Our a is 0 plus, we're going to have k minus 1, and delta x was 1 by 25, right? So this is what? 1 by 25 k minus 1 by 25. How did they get? They got it to one term. We look at one other thing. There it is right there, right? So then f of that. Okay, I want to see the alternate, all right? Oh, but then they did the right Riemann sum with that one. Okay, maybe that's why we're having a hard time, because we're trying to use the technique that they did for the right on the left. Because they got that 0.04. Because I think if we did the right Riemann sum, that would change. So where we're getting stuck at is right here. Okay. I'm just gonna have to use theirs for now. I think I'm totally burnt. So let's see. So right here, 0.04, right? If we do f of that, so for instance, that's going to be what, all of that cubed. It might just take considerable, like I might be underestimating the calculation that it takes. Like if we do f of that thing there, the circle, because like we would have to expand the binomial, right? I can't see any, because it's not a quick way to do that I see. I know we can move that 0.4 to the 4. Yeah, but we'd have to evaluate that Riemann sum, okay? I'm going to have to stop there. I have to come back to it, okay? All right, well, I'll keep looking at it, and I'll, if I can kind of get all the details, I will. But we're actually going to end the session there, okay? And from one beautiful mind to another, enjoy the rest of your day. I was looking for my headphone. Oh, I think it's still part of the same stream, which is actually awesome. I'm just checking my volume. Can't find my headphone though. Give me just a moment for this to get caught up. Maybe not. I know it's probably like a feedback or whatever. Like I said, I can't find my headphones. Is this did it restart or? Okay, that's all I needed. I just needed to know that the micro was okay. And I think it's still part. Only other thing I'm not sure if it's still part of the same stream or not. Let me just check here really quickly. It looks like it is though. Okay, so I'm just gonna assume that it is. Okay, so yeah, sorry about that. I had to step away. So yeah, as soon as I stepped away though, I saw something. It's right here. It says that they got this number that you see here. This number, it says with a calculator, right? Because I was like, I mean, it can be done by hand, but I kind of paused for a moment. One, I was like, I just need to step back for a moment. Right. Let me turn this down some more. Where did my headphones go that fast? So for instance, because it was x cubed, And we had this extra term here. Trying to cube that was like cubing a binomial, and that was going to be like a lot for no reason, right? So then I was like, well, how are they getting this number? And I was like, oh, they used a calculator, which is fine. So this can be evaluated in a calculator, and then we can produce this. All right. So then this is what for the left Riemann sum. But then the right Riemann sum is a little bit different, right? So for the left one, we had this extra term here. For the right one, if we use x of k star is a plus k times delta x, it simplifies down to this, because the a was 0 and the delta x was 1 by 25, so we just have the one term. So then when we do the sum as k goes from 1 to n of f of x sub k star times delta x, it becomes just f of this 0.04, but then that appears like that one can actually be right here, right? So when we cube it, when we plug it into the function, then this one we can actually simplify it like manually. Like, let's see, did they do that? Yeah, we could distribute this 0.4, right? So then you have this thing cubed times 0.4 plus this. But then now we have a 0.4 to the power of 4, which we got, times this k cubed, right? So then now we can use the power rules that we had just introduced, because we didn't have that extra term. That's why this one was easier to kind of go forward with. So then this one becomes right here, the 50 squared times 51 squared over 4 times this 0.04 to the power of 4 plus this 0.04, right? That one is much easier to get down to here, okay? Again, we could confirm the result using a calculator. All right, so integration, that was really just an introduction. I didn't realize it got like that, but again, that's the reason I be struggling with these, because I don't look at them in advance. I be doing them off the fly, right? So usually, with calculus, it's to be expected to get stuck, but that's okay, And I think it's important to just see that stuff, just to, know that it's not always easy, But in my opinion, it does get easier, because using the Riemann sums in that fashion, that's really more for conceptual, but integration goes a lot easier. The same way we had shortcuts for derivatives, there are shortcuts for integration, right? And it's typically not like that. So the whole Riemann sum is like in algebra when we were doing the difference quotient to introduce the derivative. So like once you get past that, to me, once you kind of start looking at the shortcuts, it gets a lot better. All right. So with that note, we're going to end the session here. I'm hoping it should be just one stream, okay? Because I did kind of stop it, but I noticed that one thing kept going, so we'll see how it turns out. But the main thing is that be sure that we've done the participation honesty quiz on Moodle. There's also an assessment on Moodle that we need to do, and then just get your assignment submitted on Pearson. So the assignments are up. I'm available for questions, and I can redo or any kind of presentation or go through any kind of questions. And I'm just here for support. Okay, I think most of you all are on your way, and you all are doing fine. Also be aware that we get a limited attempts at all assignments, and I've reduced the late penalty from 20% to 10%. So if you want an A on any assignment, honestly, it's there. Okay, if you really want it. Okay, again, on that note, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Peace.